So now we can actually take a look at some of the typical bending moment and shear force diagrams that we typically come across. And the reason these are actually important is because these are the actual real life structures which we typically deal with. I mean, we don't really deal into very advanced type of I mean, for example, let's say if it's a simply supported beam. I mean, most of us would think, okay, this is a very basic type of beam, but then in reality, like most of the structures that we typically see, say in a building or a commercial building or airports and things like that, they're actually say single span or multi-span beams. So that's the reason I just wanted to kind of cover like some of these aspects here. So first of all, let's just consider, say, if it's a simply supported beam and then we have, say, a concentrated load acting. So what we would see is more often than not, like the maximum moment which is produced in the beam would be under the point load itself, right? So that's one thing. I mean, whenever we're coming up with a shear for a bending moment diagram, and then if there's a point load, we always need to like see, and obviously this is for a pin to pin support. So in that case, the maximum moment produced is only at where the concentrated load is acting, and that's what this bending moment diagram here kind of indicates. But then when you look at the shear force diagram, so over there, what we are seeing is like we have a drop in the shear force right at where the point load is acting, and that drop is basically nothing but equal the magnitude of the drop from, say, this point here to this point. That's nothing but the applied load. So whenever you see a point load in any beam, that means whenever you look at the shear force diagram of that beam, so the drop in that shear force diagram, or I mean, that has to be the magnitude of the drop has to be equal to the applied concentrated load there. And then similarly, now this was for a pinned beam. Now if you consider, say, a fixed beam wherein both the supports are actually fixed. So in that case, this is kind of the bending moment diagram we typically have. So where we have a point load acting at this point here, but then for a fixed condition, we can't always guarantee that the maximum moment in the beam is developed over here, because so there'll be a negative moment and then there'll be a positive moment based on the sign convention that I had told. So the maximum positive moment would definitely be where the point load is acting, but then the negative moment here, the magnitude of the negative moment could actually be more than the positive moment magnitude, and that's actually applicable for a fixed beam condition. But then if you look at the shear force diagram, that's more or less similar in terms of like you will have a vertical reaction there, you'll have a vertical reaction here, and then there'll be a drop in the shear force, a sudden drop in the shear force, and that's because of a presence of a point load. So whenever we see a sudden drop in the shear force diagram, that actually indicates there is a concentrated load present over there, right? So that's what I'm trying to kind of emphasize over here. Now the second would be, say, if we kind of consider a cantilever beam. Okay, so if you have a cantilever beam subject to just one single point load, say at the free end, in that case your bending moment diagram would be more of a linear varying diagram, which is just continuously increasing. So from zero it increases all the way to the maximum value near the support, but then the shear force is actually constant along the entire length of the cantilever. And then one more thing I would like to highlight here is, as I mentioned before, like the slope of the bending moment diagram actually indicates the shear force. So since the bending moment diagram here is actually kind of a straight line, so that's the reason the slope of this is actually a constant, right? Because that's a straight line. So the slope of that is constant, and that's the reason you see a constant shear force over here. Now similarly, now if you go to say a cantilever beam which is loaded intermediately, so beyond the point of application of load, there is no response from the structure at all. It's just zero moment all the way till this point, and only after this point it starts introducing that bending moment, and then goes all the way to the support. And then similar thing happens to the shear force diagram as well, wherein if you see here, like all of this shear force is actually zero, but then beyond the point load you are actually getting the constant shear force diagram, and the constant is because of a similar reason, because the bending moment here is kind of that's actually a straight line, and the slope of that is constant. So that's one thing. Now if you consider, say, a cantilever which is subjected to, say, 2 point loads. Okay, so in that case, if you see here, we don't have so it starts with zero. I mean, it just keeps increasing with a constant slope, and then it comes across another point load here, and the slope now increases. And the reason for that being, the shear force in this section is more than the shear force over here, because the shear force over here is equal to the applied load here, but then the shear force acting over here is actually a cumulative force, which is this plus this. So that's the reason the shear force here is increased. That's what we see in over here. Like you see a constant shear force here, and then a sudden jump in the shear force which continues to be like that till it reaches the support. and the jump over here is nothing but that's equal to the applied force there. And then, as I said, like since the bending moment diagram slope actually represents the slope, so the slope of the bending moment diagram rather represents the shear force. So since the shear force over here is less, this line over here is actually not as steep. But then once you reach this section here, which is beyond the this load here, in that case, since you have a higher shear force, the slope of this bending moment diagram also increases, and that's the reason you see increased slope here. So even though these are really basic, but these are very fundamental things and very minute things to be aware of, so that whenever we are coming up with any bending moment diagram or shear force diagram, these are the things we typically try and want to QC, so that we make sure, okay, these are the aspects which are actually covered. Now the next step being, say if you have a cantilever beam which is subjected to a concentrated moment, say at the free end, in that case, along the entire beam you have actually a constant moment which is applied, or constant bending moment. And since the moment is actually fully constant, so therefore there is no variation of moment along the length of the building. So the derivative dm dx, that's actually equal to 0. And that's why you see in the beam there's no shear force developed. So these are some of the basic and very fundamental stuffs, but these are very important because this is what we typically use in our real life structures. I mean, most of our real life structure is nothing but a system of these kind of single span conditions, or maybe some multiple span conditions. Now let's kind of just take a look at an example of a multiple or a two span condition here. So for example, this condition over here, what we see is a two span beam which is subjected to 2 point loads here, like one on this side, one on the other span. So the thing is, like, and we have an intermediate support over here, so obviously there's a continuity of the beam over here, and that's the reason the kind of bending moment diagram we see here is it is 0 over here, because at this point there is no rotational degree of freedom which is being restrained, same as here. But then one would argue even this one is a pinned, so this should have no bending moment, or there should not be any support reaction here, right? So I mean, yeah, that statement is correct. So this diagram that we are seeing here is actually the bending moment diagram. So this is not the shear force diagram. So this is the moment which is actually developed within the beam itself. These are not the moment which is developed on the support. So that's the reason, like, you see a negative moment over here. The negative, I am saying, because what I said before is in terms of sign convention is bottom is tension, top is compression. So that's the reason, like, this one is seeing a positive moment. But then as you move towards the support, the this kind of restrains the movement of this beam downward, so it actually is trying to pull the beam upward. So that's the reason it kind of develops this kind of a curvature where the tension is at the top and compression is at the bottom. And then once you start to moving towards this kind of support, this support here, again it's back to say a positive moment here, where, and then again if you see, like, this point load here, that's where you see the one of the maximas in the moment diagram. And then if you see here, you see a maxima in the negative moment, and then once you go over here, you again see a local maxima here as well. But in terms of magnitude of these moment, like this moment versus this moment versus this moment, all of this is actually a function of the stiffness of these members and the spans of this member. I mean, for example, if this one is a 10-meter span, this one is a 20-meter span, it could be that this moment is higher than this one here, or maybe this one here as well. But then if you have, say, a 20-meter span here and a 5-meter span here, in that case obviously this moment will be much higher, because we know, like, longer the spans, the higher the moment that span actually attracts. So that's one aspect. And then if you look at the shear force diagram here, so the thing is, like, whatever supports we see here, they're actually applying these vertical forces on the beam, right? I mean, if you consider the free body diagram of the beam, so these supports could be replaced with vertical forces on the beam itself, so that this beam is actually in equilibrium. So when you look at the shear force diagram, you see a concentrated force here, right? So that's the reason this jump here, and there's no intermediate loading here, so that shear force remains constant. And that's what we see here, like, that's a straight line, so the slope of that would be constant, and that's the reason we see a constant straight line here. And then once you apply a point load here, we see a sudden jump in the, or sudden drop rather, in the shear force. And then the shear force becomes negative. If you see the slope over here and the slope over here, there will be different in sign as well as magnitude, right? So that's the reason. I mean, for example, if this one is having a negative slope, so this shear force is kind of negative, right? But then this one is having a positive slope, so that's the reason this one is a positive shear. So that's what also we kind of see here, right? So whenever we apply a point load there, that's what actually happens. And then once you reach this support here, you again see a point load which is acting vertically upwards. So that's another concentrated load. That's the reason you see a jump over here back in the shear force, right? And the jump over here, like, from measure from this lowermost point to the highest point, that's nothing but that's equal to the vertical reaction that this support is inducing on the structure. and then so on and so forth. And then once we move to say this point load here, the force is actually constant till we reach this point load. And then there's a sudden jump again over here, and then we move back to this support, and then we see this reaction here. So this is kind of what happens, say, when you have a multiple span condition, and then you have like three stiff supports. But now if you look at this diagram to the right, where what I've done is like I've actually replaced the intermediate support, say a fig pin support, with a spring. So what I've done actually here is I've introduced some kind of a flexibility in this support here, right? What this pin over here was doing is it was actually very effective to, control the vertical movement of this beam, so that, the vertical movement or the vertical deflection of this beam at this point is zero. When you move to this support here, that's not actually equal to zero, but it will have some deformation, and that deformation multiplied with the stiffness of the spring, that's actually going to induce the vertical stiffness or vertical reaction here. So if you look at the bending moment diagram here, that's still similar to what we see here, but the difference is, in the magnitude of the moment that you see here versus here. So for if everything is the same, in terms of say loading and span and everything, so if you were to compare this structure with this structure here, the vertical reaction induced in the structure in the left will be higher compared to that in the right, and therefore the negative moment that's induced in the beam over here is actually much small, or maybe small compared to this one here. And then as you keep increasing the flexibility of this spring, or in other words, if you keep, reducing the stiffness of this spring, in that case, what's going to happen is this negative moment is going to, keep dropping down, and then there might be a point where it's again a positive moment here and not a negative moment here. And this moment over here, the magnitude of the positive moment here actually increases compared to this one here, because that load is now being redistributed to these supports and these spans. So that's what happens here, and this is important in real life, because in real life, say if you have considered, the structure to the left, so you have overestimated the negative moment that the member is seeing over the support, but then the positive moment here is kind of, underestimated. Versus if you go to this support or this structure here, you are underestimating the negative moment here, but you are capturing a higher positive moment here, right? So in design, just to be on the safe side, we just kind of, consider the envelope, say, where you consider this negative moment for, design of the member for this negative moment, and then when you are considering the positive moment here for design, you actually consider this moment instead of this, just to kind of envelop the scenario and to be on the safer side. So that's what's kind of typically done. I mean, this is something which we actually apply on a real life projects every time, this kind of principle, just to capture, the worst case scenario, and this is known as enveloping. So after beams, we can actually just quickly move into, some structure which is also known as frames. So that a frame is nothing but, or portal frames. A portal frame is nothing but, a system of beams and columns which are connected together. So this is a very basic, single storied, single span portal frame, wherein you have a beam which is shown in green, which is connected to these vertical members which are known as columns. So the load path here is like whatever load the beam sees, it just transfers that to the column, and then from the column the load actually goes to the foundations, right? So that's what this is. So we'll just go through quickly like different types of portal frames that we typically encounter. So for example, say this one is first one, which is the basic one, say a single bay and a single storied, portal frame. Then we have two bays. So we have one bay here, the other bay here, but it's a single storied portal frame. So that's another type of portal frame here. Then we have a single bay, but two storied, right? So we have one story here, the other story is here. So that's like a two storied single bay portal frame. And then we have like two bays and multiple stories. I mean, if there's no stories like more than two, in that case we just call it a multiple story frame. And then you could also have, a bunch of moment frames in series. I mean, say if you have a single storied building, but then you have a bunch of moment frames here, or portal frames here. So even that's a possibility. And then you could have this kind of, scenario as well, wherein you have multiple bays and then multiple stories, right? So just wanted to touch upon some of the different types of portal frames around that we have. And these are actually real life structures as well, because if you consider any typical building, for example, say a typical RCC building, so that is basically a series of, system of beams and columns. So this kind of structure is very common, that's used. So just some of the common bending moment and shear force diagrams for this kind of structure as well. So say you have a portal frame, wherein the bases of those columns are actually pinned, and then you apply, say, a lateral load, which could be due to wind or seismic or whatever. So in that case, this is the kind of bending moment diagram that we see. And I mean, one thing which I would like to mention is, like, whenever you have to derive any bending moment diagram, always look at the reflected shape of the beam or the structure, because that gives you the kind of curvature that the member is going to have, and that lets you know, like, okay, where you will be seeing, tension at top and tension at bottom and things like that, and therefore you can come up with the bending moment accordingly. For example, if you apply a point, lateral load here in this portal frame, what you would notice is, like, this column here is kind of, flexes, so that there is tension on the inside face of the column, and then there's compression on the outside face. So that's what this bending moment is showing for this column. And then once you go to the beam over there, so the beam would be such that there is tension at the bottom, and then compression at the top. And then these moments which are developed in the columns and the beams are such that the joint over here is kind of an equilibrium. So by that, what I mean is, the bending moment in the column over here and the bending moment in the beam, they have to be equal in magnitude for moment equilibrium of the joint. So that means, for this example over here, like, the moment induced in the beam at this joint and the moment induced in the column at this joint is actually equal in magnitude but opposite in sign. And then once you move to this joint, so if you see here, like, when you apply this lateral force, so this is the bending moment that's developed in the beam, which is going from a negative value to a positive value with a constant slope over here, because there's a constant shear force that's acting on this beam, which we are seeing on this side over here. And then once you reach the column over here, you again see, this bending moment over here in the column joint, and then as you go down at the pin, it actually reduces to zero, right? So what I'm showing here is basically a single storied portal frame, which is subjected to, a point load in the horizontal direction. And then the one below you see is again the same portal frame, but then you have the column bases fixed. So if you see the bending moment diagram, what has changed is, there's this moment which is also developed at the column bases, which was not there here. And this is kind of, the column bending moment diagram and the shear force diagram that we see, right? And then the shear force that we typically, so from a shear force standpoint, so whenever you apply any point load, obviously you are going to see these horizontal reactions on the support, right? So that horizontal reaction that's developed on the support, that's nothing but that's equal to the shear force, or rather the shear force in the column is actually equal to the horizontal reaction that's developed in the support. So for example, if this was a roller support instead of a pinned support, in that case, the entire horizontal reaction would be taken by this support, and there would be no horizontal force or reaction on the support at all. So that means, like, there will be like zero shear force on this member, and the shear force here will be equal to, the total lateral force that's applied. So just wanted to let you know, like, how we come up with, like, how does the moment or the shear force in the column relates to the corresponding reaction at the column. And then something similar happens here, right? Where if you have a column which is fixed at the base, in that case you will have a moment reaction here, and then you have a shear as well. So you will see that there is a shear force developed here, which is equal to the horizontal reaction at the support, and then the moment reaction that's developed here, that's actually equal to the bending moment of the column at the base, and then it just keeps changing linearly, because, and the slope of that linear diagram is nothing but that's equal to the shear force that's developed here. So it's the same principle, which is, slope of bending moment is equal to the shear force. So that's the same principle that's applied here as well. The reason I'm saying all of this is because, like, including the I mean, even the boundary conditions here actually are very critical for a frame. So for the same frame, if you had a pinned support versus a fixed support, you see different behavior of the structure, right? So that's that. Now the thing is, if you, and in addition to the lateral load, you also see those gravity loads, right, that we talked about before. So in that case, this is kind of the bending moment diagram that we typically see for a pinned base frame, where what you would see is, like, there's a negative moment that's developed near supports because there's fixity, and then you see like this kind of a diagram which we also saw in a continuous beam, and then after that there's this moment over here which is developed in the column, which is equal to the magnitude of the moment developed in the beam here for equilibrium of the joint, and that reduces linearly to zero moment here because this is a pinned support. And this is kind of the shear force diagram that we see here for the column here. So if you see here, I mean, the thing is, like, even though we are applying a vertical load, we're still seeing horizontal force here. And the reason for that being is because when you apply this kind of load here, the columns actually want to, move outwards. But then since this is a pinned support, that's actually restraining that movement, and therefore it develops those reactions in the horizontal direction. And that's the reason we see this shear, developed in the column, which otherwise we would not have expected. And then something similar that we are seeing here for a fixed base moment frame. So all of this was for a single storied structure, and then we have, like, something similar for multi-storied multi-bay portal frame as well, wherein say if you consider real life building, I mean they're more like something like this, wherein you have multiple bays of portal frames and then you have multiple stories, and then at every story you apply these lateral loads, be it wind or seismic or whatever. So this kind of moment frame is actually, or rather this kind of moment diagram is what we typically see in a real life building, wherein whenever you apply this load, like you see this kind of, so whatever I've shown in green, that's nothing but the bending moment that's developed in the columns. And then whatever is in blue, that's something that I'm showing as a bending moment diagram of the beam. So that's what we typically see for lateral. And for gravity load, say if we consider all of these floors to be, loaded vertically, in that case, this is the kind of bending moment diagram we get in the beams, right? But and then in reality, what we do when we design these structures is we just have those different load combinations based on the different design codes. So we just combine, the left diagram with the right diagram based on different load factors. Say if it's a dead load plus wind load, so in that case, say the load combination is 1.5 wind. So in that case, what we typically do is we just come overlay or rather superimpose this bending moment diagram scaled up to 1.5 factor, and then add that or superimpose that with this, bending moment diagram here, and then come up with what's the maximum demand that any beam sees at any section, and then ultimately, design the members accordingly. But and then this one here is basically for a fixed base condition of the columns, wherein if you see again for what we saw in the single storied portal frame, that we have a similar observation here as well. I mean we have these base fixities or base fixed moments that's developed here based on the because of these horizontal forces, and then we have when we apply these vertical loads, we also have these bending moment diagram that's developed in the beams and also in the columns. And then again, similar to what we just said before, like all of these are actually combined together or superimposed to come up with the final design aspects. So these were the few items I just wanted to kind of touch upon in terms of the bending moment and shear force diagrams. I mean, obviously this is not really a all exhaustive type of loading. I mean, for example, I just considered the point loads as of now, but then a structure would also see a bunch of uniform distributed load, and that's what typically dead loads and all would be. So they have a more or less similar type of behavior, but the only difference would be like here we are seeing these discrete lines, but then when you consider a uniform load, in that case this will become more like a nice curved type lines. And the reason for that being is if you go back to the differential equation that we were talking about, right? The del 4 y over del x4 is equal to loading intensity over ei. So since here there's no loading intensity as such, we don't see that continuity, but once you come up with those linearly varying load or maybe uniform load, you will see much more kind of curved type of bending moments instead of these bunch of linear lines here. Now we can actually quickly just touch upon what are different roles and responsibilities that one would expect an entry level in this industry. When you're just entering the industry at the entry level, so more like at a graduate engineer level or a EIT or engineering trainee level. So the kind of tasks that you are typically expected to perform is the analysis and design of elements, which means like you have to just develop your analysis models, you have to apply loads, you have to analyze those structures and then design those elements, and then obviously have to discuss with the supervisor and all, like if things are making sense. But that's kind of one aspect of the entry level task. The other would be say construction administration task, wherein you'll have to review some of the shop drawings and then also say answer some of the RFIs which are coming from site. So construction administration is more something which is helping something to be done on site. So based on whatever drawings we had published, so based on that, the fabricator or the contractor actually interpret their stuff, and then they publish their drawings and then share that back to us based on their interpretation of our drawings. And then we kind of make sure like whatever they have interpreted of our drawings is actually correct. I mean that's what an entry level guy would also kind of do. In addition to that, some quantity estimation task as well, or BOQ as they call, like bills of quantities, and also wherein you have to make sure like whatever, say it's a RCC building, so whatever kg per meter cube reinforcement that you're using or whatever kg per meter cube of slab you're using and things like that. So, I mean the concrete quantities, the steel quantities or whatever. So that's something we have to, we have to do kind of so that to make sure like whatever we are doing is in line with what was expected. And then also we might be able to ask to develop some tools to make the productivity a bit more better. And then lastly, some site visits that you might be able to go for. And then now let's just quickly touch upon the roles and responsibilities at a senior level. So at a senior level, I mean the kind of position you will be at is so the senior engineer or the assistant manager or the design manager area. And then your roles and responsibilities more kind of interfacing with the clients in terms of say you'll have to coordinate with other trades like mechanical or architecture or plumbing, guys or the underground utilities, and just make sure like whatever structure we are coming up with, there's no clash or anything with them. We have to have a bunch of coordination meetings with them to make sure like there's no clash or anything, or if there's any clash at all, if there's identified a clash, then in that case what kind of solution that we can give, so that as I said before, like the structure and the other trades could actually live in harmony for the success of the project. And then we also kind of as a senior engineer, you're also expected to kind of lead a team of engineers to deliver projects. And then you also need to kind of validate the quantities and QC the work that was done by the junior level guys, so that we need to make sure okay whatever the junior guy is coming up with is kind of making sense. And then address some complex issues identified on site. Maybe on site there is some issue, say the concrete that we had the design concrete strength that we are targeted for, that's actually not achieved, or maybe there are some other issues that have been identified on site. So the senior guy is supposed to kind of identify those and then address those accordingly. And then also, we need to also start networking and becoming visible among competitors and clients, so that ultimately when you go to the top management level, you're able to bring in projects for the company. And then once you are in the top management, basically you're either a project manager or a managing director of a company and things like that. So over there, you basically are expected to handle the project financials, whether the project is actually making loss or profit and things like that, and just keep track of that. And then make sure like whatever project you're working on is making profit for the company. Then work on some business development aspect, wherein it's basically getting more and more projects for the company, and then have that proper networking with the client, so that you get recurring business from the same client, or maybe get new clients and all. Then some of the office and company budgets and things like that. So that's what you're expected to do when you're in top management. And then creating the vision, core values of the company, etc. And then lastly, maintaining a professional relation with the potential clients for healthy business. And I guess lastly, what I would like to touch upon is just some of the common sectors that we typically, any structural engineering firm that commonly deals with. Say we have aviation, wherein we're talking about airport terminals or concourses, and then we have sports, like the sports stadia or stadia roofs, and then we have parking structures, wherein we're talking about parking garages or contracts, and then we have healthcare projects like hospitals or maybe outpatient clinics and things like that. Then we could have amusement parks or theme parks or convention centers. Then residential, wherein which is really common in India as well. Like most of the structural engineering firms are actually working on the residential buildings. And then lastly, some of the hospitality aspects like hotels, schools, etc. So yeah, I guess that's what I wanted to cover for today. Thanks a lot for hearing me patiently.